In this example, we have kerosene flowing through a Venturi tube. We want to determine the pressure difference at the flow rates given, which are here and here. And we're also going to assume this is an ideal meter. So we're going to assume that the coefficient of discharge is 1. If this was a real meter, we'd have a coefficient of discharge of probably like 0.95 or something like that. But we're just going to do this with the ideal meter. So as we take a look at this, what we'll do is we'll take a look at what our obstruction meter equation is. And so we've already calculated that as Q is equal to CD, area of the throat, times 2 times the pressure difference, P1 minus P2, over the density of the fluid, 1 minus beta to the 4th. We're taking that all to the 1/2. So we do want to get this pressure outside of it, so what are we going to do? We're going to square everything, and then we're going to multiply everything through. And so once we do that, we'll get pressure 1 minus pressure 2, isolated on this side, is going to be equal to Q squared divided by CD squared AT squared. So that takes care of all that. And then we're going to have rho over 2, 1 minus beta to the 4th. And we do know, or we can easily find all the stuff on this side. We know our discharge coefficient is 1. We can calculate out beta. So what's beta going to be? So if we go back to this picture, beta is going to be 0.1 meters. Sorry, 0.06 meters divided by 0.1 meters, so D2 over D1. So 0.6 meters divided by 0.1 meters. And once we do that, that'll give us 0.06, dimensionless parameter. And so for there, let's plug in our numbers for the first flow rate. So Q squared is 0.005 cubic meters per second squared. CD is 1, so we'll just drop that out because 1 squared doesn't matter. For area 2, we've got pi over 4, 0.6 meters squared. And then we're going to multiply it by the density of the fluid. So if we look in the problem, it doesn't give us a density, but does give us a specific gravity of 0.85. How do I find density? Well, specific gravity is the density of the fluid divided by the density of water at 4 degrees C. Density of water at 4 degrees C is 1,000 kilograms per cubic meter. So when I do that, that's going to give me a density of 850 kilograms per cubic meter. So 850 kilograms per cubic meter divided by 2, and then 1 minus 0.6 raised to the 4th. Unitless parameter on that side. Let's look over here. I've got cubic meters per second. I've got meters to the 6th per second. So we start knocking those units out. So I'm going to be left with, let's see, 3 there, we'll knock out 3 there, 2 there, we'll knock out 2 of those there, which is going to leave me with meters. So I've got meters per second squared times kilogram. The kilogram meter per second squared is a Newton. And 1 second. And I waited a second because, once again, using units, you'll figure out when something's incorrect. Because as I was doing that, I had kilogram meter per second squared, which would be a Newton. I should be expecting a Pascal. So I look back through my equation and go, oh, you know what? I forgot to square my area. Once I square my area, that's going to leave me with newtons per meter squared, which is what I expect. This is why units are really important, because you can catch things like this, you can catch mistakes. Pressure 1 minus pressure 2. I've got everything in there. My units are going to work out right. I plug everything into my calculator, and I'm going to get 1,000 160 newtons per meter squared, which is 1.16 kilopascal. So there's my first answer. So now let's look at the second flow rate. And so that flow rate's 10 times faster. So P1 minus P2 is going to be equal to 0.05 cubic meters per second squared divided by pi over 4 times 0.6 meters. And then we're going to square that. Or 850 kilograms per cubic meter divided by 2. Yeah, I don't know if you heard the barking, but my dog was sitting at my feet and the garbage man just went by. So anyway, back to our example. And then 1 minus beta to the 4th. Unit-wise, we look at them this time. Everything, we have it the same as the one before, which is good. So we have the correct equations. So now when I multiply that through, I'm going to get 116,000 newtons per square meter, which is 116 kilopascals. So the important thing to note here is we had a 10% increase in the flow rate. But to get that 10% increase in flow rate, we had to increase the pressure difference by 100 times.